Hi everyone, welcome to this session on ZGC. My name is Per Liden. I'm part of the Java Platform Group at Oracle. This talk is divided in two main parts. In the first part, I'll talk about what ZGC is, how to use it, show you some performance numbers. And in the second part, I'll talk about our roadmap, more specifically about the work we're doing to make ZGC a generational GC. Before I begin, I'd just like to remind you that you should have a chat box next to the video stream, so feel free to ask questions there during the talk, and we'll do our best to try to answer as many of those as we can. Okay, so this is how we describe ZGC in one sentence: a scalable, low-latency garbage collector. And to get a better sense of what we mean with scalable and low latency in this context, we can have a look at some of the properties of ZGC. So when we're talking about latency, we're referring to GC pulse times. And ZGC is a sub-millisecond max pulse time GC. So you'll never see a GC pulse longer than 1 millisecond. When we're talking about scalability, we're referring to heap sizes. So ZGC can handle heaps ranging from very small, like a few hundred megabytes, to very large, like multi-terabytes. And the important thing to know here is that it can handle these multi-terabyte heaps while maintaining the sub-millisecond max pulse times. So what's the catch, you might wonder? Well, as always, there are trade-offs. And for ZGC, you should expect to see some amount of throughput reduction when comparing ZGC to parallel GC or G1 GC, which are more throughput-oriented GCs. So how much reduction should you expect? Well, it's hard to give a generic answer to that because it very much depends on the workload, but expect to see a few percent, maybe 10% in some cases. And in some cases, you won't see much reduction at all. So ZGC is designed to be easy to tune, and preferably you shouldn't have to tune it at all. This is a goal we've had with ZGC since its inception. As you know, Hotspot has a lot of GC tuning options. Sadly, not that many people know exactly what all of those options do. Many times we see people getting them wrong, and we want to get away from that situation by essentially making ZGC work well out of the box. This is a list of the GCs available in Hotspot today that Oracle supports, and we can see here how ZGC fits into this picture. So we have serial GC, that's a GC optimized for low memory footprint. So that's something you might see being used in a very small container or an embedded system, something like that. We have parallel GC, which is a throughput collector. We have G1, which is the default GC since JDK 9. That's optimized for, or that tries to provide a good balance between throughput and latency. And then we have ZGC, which is optimized for low latency and addresses that part of this spectrum. The most important thing perhaps to know about ZGC is that it's a concurrent GC. So that means that it's collecting garbage while Java threads continue to run. There are still a few pauses, but those are very short, and no actual garbage collection activities goes on there. All of that happens concurrently. It's a tracing GC, which, or like all GCs in Hotspot, it will actually traverse the object graph on the heap to figure out what's live and what's garbage. It's compacting, so it will be moving objects around to fight fragmentation, so that it's able to free up large contiguous chunks of memory. It's currently single generation, and we'll get back to that in the roadmap part of this talk. It's region-based, which means that the heap is divided into many smaller regions. G1 is another example of a region-based GC. And this allows for some flexibility, and for example, it allows the GC to focus its activities on regions which has the most garbage, and hence collecting those will give the most bang for the buck. ZGC is NUMA aware, which means that whenever a Java thread allocates an object, that object will end up in memory that is local to the CPU this Java thread is executing on, and thereby will get the best memory latency when that object is later accessed. ZGC uses load barriers and colored pointers. That's the two main techniques to achieve concurrency and allow for garbage to be collected while Java threads are still running. Another important thing to know about ZGC is that pauses are O1. In other words, they execute in constant time. So it doesn't matter what heap size you have or number of threads your application is using, or any other resource like that. None of that matters for the pause times. They remain the same. Should be perhaps good to know that ZGC is still at the mercy of the operating system scheduler, so you might still see some variance in pause times due to scheduling latencies and so on. ZGC is available on all common use platforms. That means Linux, Windows, Mac OS, on Intel x86 and on ARM. And on Linux, there's also support for PowerPC. ZGC initially came in as an experimental feature in JDK 11. However, a few releases later, in JDK 15, it was declared production ready. So that, of course, means that we encourage you to use this in your production workloads. And yeah, should you run into problems, of course, Oracle would happily offer you support. Let's have a look at some performance numbers. So here we have Spec JBV 2015 showing you the benchmark score. This is an industry standard Java benchmark that produces two scores. That's max JOPS, which is a throughput score in green here. And we have the yellow bars, which shows you critical JOPS, which is a latency score. And here we're comparing ZGC and G1 with a heap size of 128 gigabyte. And as we can see, G1 is ahead by a few percent when it comes to throughput. On the other hand, ZGC is well ahead when it comes to critical JOPS, the latency score. Maybe even more interesting is to look at the GC pause times for this benchmark. So that looks like this. So the scale here is in milliseconds, and we see that G1 has an average pause time of around 150 milliseconds, a max pause time of about 450 milliseconds. And ZGC pauses don't show up here. And that's not because I removed the data or the bars here. It's just that they don't even register on this scale. So if I zoom in by a factor of 1,000, it looks like this. And now we can start to see ZGC's pauses. And if I just remove the magnifying glass here, it looks like this. So I've zoomed in by a factor of 1,000. In other words, changed the scale from milliseconds to microseconds. And then we see that ZGC has an average pause time of around 30 microseconds, which is pretty nice, and has a max pause time of 200 microseconds. So well below the 1 millisecond target. And I hope you can see what this could mean for your application. If you today have an application that struggles to meet response times requirements, then switching to ZGC might be the thing you want to do. Here's another benchmark called the Big RAM tester. That's a GC stress test. It causes a lot of heap fragmentation, so the GC is constantly busy moving objects around to fight fragmentation. And the story here is pretty much the same. G1 has an average pause time of around 250 here. ZGC pauses don't even show up. And again, I need to zoom in by a factor of 1,000. In other words, convert the scale from milliseconds to microseconds, and we see ZGC pauses averaging of around 50 microseconds or so. Max pause time around 200 microseconds. So again, pretty nice. Here we see ZGC improvements over time. So as I mentioned, ZGC initially came into the JDK, or initially came into JDK 11, and it has improved since then for every release. And here we can see, roughly these scores here have improved by about 10% or so. Maybe even more interesting is to look at this, how pause times have improved over time. Here we can see that back in JDK 11, where ZGC was experimental, it struggled a bit here, had a max pause time of almost 5 milliseconds. But since then, a lot have happened and things have improved. And nowadays, pauses are constant and they're essentially well below 1 millisecond and essentially a non-issue for most applications. This is, again, same benchmark showing you improvements over time, but this time it's executed on a much larger system, just to show you how scalability have improved. Here it's using a 3 terabyte heap, and the system has more than 200 hyperthreads. And again, back in JDK 11, ZGC struggled to handle this system, pause times approaching 20 milliseconds, completely unacceptable, of course. But since then, things have improved. Pauses are nowadays constant. So in JDK 17, again, the size of the system doesn't matter. They're all well below 1 millisecond. Okay, a few words on using ZGC. So there's this option called Use ZGC, similar to how you enable other GCs. Then we come to tuning. And as I said in the beginning, we've been working hard to try to make ZGC easy to tune. So the main tuning option you want to look at and set is the max heap size. So what should you set this to? Well, the max heap size obviously need to be large enough to accommodate the live set of your application, first of all. But then you also need to have a certain amount of headroom in the heap. And that headroom will basically dictate how often the GC needs to run. But we should also remember that this is a concurrent GC, so you need to have enough headroom to allow for allocations to happen while the GC is running. And if this headroom is too small, and then there's a risk that the application can basically outrun the GC by producing more garbage than the GC is able to collect. And if this happens, then you might eventually run into an allocation stall, and that's a bad thing. That means the JVM had to temporarily stop allocating Java threads to allow for the GC to basically catch up. So that's something you want to avoid, and you avoid that by increasing the max heap size and give ZGC more headroom. So in summary, you want to give ZGC or the more memory you give ZGC, the better, but at the same time, you don't want to waste memory. So it's all about finding a balance between memory usage and not running into allocation stalls. That's the main configuration option I would recommend you to set. There are a few other options too, like fiddling with number of threads ZGC is using and so on. At this time, I don't recommend you to fiddle with those unless you really, really have to. If you want to enable logging, I would recommend you to use one of these two options, xlog::gc, that will give you basic logging. So one line of output per GC happening with just some basic information. But then if you want more detailed information on what's going on, then you use the xlog gc star. And that's something you want to enable if you are curious and how, more details on what's going on under the hood. If you're running into problems, if you're sending a log to someone to analyze, then you want to have the detailed view. Okay, so let's talk about the roadmap. And as I said in the beginning, this will be about our efforts to make CDC a generational GC. And I should perhaps say that keep in mind, this is work in progress. So everything I'm going to say here is basically subject to change. So start with the basics here. A generational GC is a GC that exploits the generational hypothesis. And this hypothesis basically says that a very common pattern, in this case in Java applications, is that most objects are short-lived. Generational GC exploits this by dividing the heap into two logical regions, and they're usually called the young generation and the old generation. So when a new object is allocated, it will be placed in the young generation. And since most objects are short-lived, most objects in the young generation, become unreachable shortly after being allocated. However, if an object remains reachable for a longer time, then the GC will eventually move it to the old generation. So when the young generation becomes full, most of the memory in the young generation will now contain garbage. In other words, objects that have become unreachable. This in turn means that the GC can now focus most of its efforts on collecting garbage on the young generation, simply because that's where it will get the most bang for the buck. And the reason for that is that there are relatively few objects still alive in the young generation, so traversing that object graph will be relatively inexpensive, and there's lots of memory to reclaim. In contrast, of course, collecting the old generation is more expensive because more objects there will be alive. So again, traversing that graph will be more costly, and the amount of memory to reclaim in there is typically lower. So the whole point of doing this is to reduce the effort needed to collect garbage. And you can look at this from a few different angles, but one is that given a certain amount of headroom in the heap, the GC can now withstand higher allocation rates. Another way of looking at it is that, given the same allocation rate, you can now lower the headroom in the heap, so use less memory for the same workload. And a third way of looking at it is that the GC will now use less CPU. So the number of CPU cycles spent per collected byte will be less. So I said that, the generation GC typically divides the heap into young and an old generation, but this is not quite what it looks like under the hood if you have a region-based GC like ZGC. G1 is another example where it would look something like this. So you have a bunch of different heap regions. Some of them are assigned to the old generation, some of them are assigned to the young generation, some are currently unused. And keep in mind, this is just a snapshot here. This is not a static assignment. Heap regions can change from young to old or free during runtime. Okay, so in ZGC today, we only have one type of collection. We collect the whole heap every time. But with the generational GC, we now have two different types of collections. They're called minor collections and major collections. Minor collection is a collection that collects the young generation. And this is the type of collection you will see most frequently. And collecting the young generation involves, of course, scanning roots to find pointers pointing into the young generation. But that's not quite enough in a generational GC. There's also something called a remembered set, and that's a data structure that tracks or keeps track of what pointers do we have in the old generation that point into the young generation, because those pointers can also keep objects in the young generation alive. So only traversing through the roots is not enough. We also need to traverse through the remembered sets to get a full picture of what's live and what's garbage in the young generation. So that was minor collections. Then we also have major collections, and that is a type of collection that first collects the young generation and then the old generation. And like I just said, using roots and the remember set, we collect the young generation, and then that's followed by collecting the old generation, and that's done again, scanning roots to follow pointers pointing into the old generation, in addition to pointers we found while collecting the young generation. We found pointers in objects living in the young generation pointing into the old generation. These two sets of pointers will give us an accurate picture of what's live and what's garbage in the old generation. Then we come to tuning. So as I said in the beginning, we've been working hard to try to make CDC easy to tune. Preferably, you shouldn't have to tune it at all. One thing that many generational GCs lets you do is configure the size of the generations. In CDC, we don't plan to do that. Instead, the size of the generations will be automatic and dynamic, meaning during runtime, they will change to best fit the current workload. There is also this thing called Tenuring Threshold that most generational GCs allows you to set. That basically dictates how old an object needs to become before it's moved over to the old generation. And again, that's something we hope to not have to bother anyone with in CDC. So that will be dynamically tuned at runtime to best fit the current workload. And finally, dynamic number of threads. We already have this feature today in CDC, but this has been improved quite a bit in generational CDC. So our hope is that you should never have to care about or think about how many threads CDC is using at any given time. The heuristics and will basically figure this out for you and make an optimal choice. So we want to reach this point where you shouldn't have to care about this, heuristics of the GC or how much resources it should spend on various generations and stuff like that. We just want you to set the max heap size, and that should be it. Let's have a look at some preliminary benchmarks. Again, a reminder, this is work in progress, so these numbers might change going forward. So here we see a diagram showing you the amount of memory needed to maintain low latency. And that means, in other words, what heap size is required for this benchmark to avoid running into allocation stalls. Here we're using SpecJBB 2005. That's a benchmark that has a very high allocation rate. It doesn't have a very big live set. So in this particular example, we're running a Java agent alongside the benchmark to inflate the live set to 1.5 gigabytes. And as we can see, non-generational CDC needs 15 gigs of memory here to cope with this allocation rate. On the other hand, generational CDC only needs 6 gigabytes. So that's a pretty significant improvement. It's a drop by 60%. Here is the benchmark score for this run, and this is maybe even more interesting. Remember, generational ZGC in yellow here uses only 6 gigabytes, and non-generational is using 15 gigabytes. Even though generational ZGC is using less memory, it actually produces a better score. And that's pretty impressive. And the reason for that is just that generational ZGC, even though it might be collecting more often because it has less memory to work with, its young generation collections or minor collections are much less expensive, whereas the non-generational ZGC is collecting less frequently, but it has to collect the whole heap every time. So it pays off even though generational ZGC has less memory to work with, and it produces a better score. Here's another benchmark called the Extreme-M benchmark, again showing you the amount of heap needed to avoid running into allocation stalls. And the story here is pretty similar to the previous benchmark here. Generational ZGC needs quite a bit less memory. It's a drop by 70%. Here is the same benchmark again, Extreme-M, but this time looking at CPU usage. So in this case, both of the GCs have been given the same amount of memory, and we just compare how much less CPU generational GC is using. And as we can see, it's a drop by about 58%, which is again a very nice improvement. All right, so if you're interested in more information on ZGC, I would recommend you to head over to the OpenJDK Wiki, where you'll find a ZGC subpage. And on that subpage, you'll find general information on ZGC, how to configure and tune it. You get other slides for other talks, videos for other talks. You'll find links to GitHub and so on. So if you want to try out generational ZGC today, head over to this page, find the link and clone the repository, and off you go. I also have a blog where I usually write posts about whenever we release a new version of the JDK, and I'll list some of the more interesting new features and improvements that have gone into that release. So if you're interested in that, head over to malloc.se. And that concludes this presentation. If you want to reach out, you see my contact information here. And before I leave, I just want to remind you that Java 18 is available now. Go download it, try it out, and enjoy the new features and performance improvements. Right. Thank you.